Good afternoon, my name is Jieun. I'm working as an assistant professor at the Eindhoven University of Technology. Today I'm going to talk about the low-frequency noise reduction by a noise barrier made of a resonator array. We can easily find noise barriers installed around traffic roads. Noise barriers reduce the level of noise that reaches the receiver by interrupting the noise propagation path. Even though they are effective at reducing high-frequency noise, low-frequency noise reduction remains challenging as sound waves at low frequencies are easily diffracted over the barrier. In the last decade, lots of research was done using sonic crystals as noise barriers. The sonic crystal noise barriers are made of periodic cylinder or other types of columns. Such sonic crystals can block the noise efficiently at the frequency range called break gap, which is determined by the periodicity of the sonic crystals. But sonic crystal barriers usually require several periods in the direction of the noise propagation, and these three as shown in these figures, which might not be suitable when there is a strict restriction of the space where the barrier should be installed. So the objective of this work is to explore the possibility of low-frequency noise reduction with noise barrier of more compact width. The configuration shows the design of the noise barrier suggested in this work. The barrier consists of cylindrical Helmholtz resonators. The resonators are attached to form a monolayer along the vertical direction. We set the height of the barrier as 4 meters and source and receiver are placed on the ground 6 meters away from the noise barrier. The outer diameter of the resonators is 20 centimeters. The inner radius of the ring is 9 centimeters. And the opening width of the slit is 2 centimeters. The graph on the right-hand side shows the noise reduction performance of the noise barrier in the frequency range up to 500 Hz, calculated by numerical simulations. The blue line represents the insertion loss by the suggested periodic resonator barrier, and the dashed black line represents the insertion loss by nominal case, which is the barrier made of rigid cylinders instead of the resonators. Compared to the nominal case, it is noticeable that there is a high peak starting at 220 Hz, which corresponds to the resonance frequency of the resonator. The increase of the insertion loss is around 6 decibels at this resonance frequency. In addition, the barrier with periodic resonators have multiple peaks with the increased insertion loss in frequencies below the resonance frequency of the resonator. In the following slide, we will explain the physical mechanism of the increased insertion loss. Before we directly explain what is happening with the periodic resonator barrier, it is worth mentioning the wave behavior around normal plane barrier. When sound waves encounter discontinuities in the propagating medium, a diffraction phenomenon occurs. In the case of the noise barrier, waves behave as if there is a secondary sound source emitting sound at the top of the barrier. These diffracted waves interfere with waves that are reflected from the ground surface. This interference of the diffracted and reflected waves forms harmonic standing wave patterns along the barrier in the vertical direction. And at frequencies where the top of the noise barrier becomes an antinode, the insertion loss slightly increases. This can be observed in the insertion loss graph of the plane noise barrier, as shown in this graph, We can see the regularly spaced small round peaks and troughs in the graph, and the location of the peaks changes depending on the height of the noise barrier. This standing wave pattern can be checked once again by the numerical simulations. I would like to mention that in this work, we use attached rigid cylinder array as the nominal case, just to give a fair comparison condition with the periodic resonator barrier. We use this cylindrical shape to develop analytical solution of the periodic noise barrier, which is not part of this presentation, but the cross-sectional shape of the resonator actually does not matter. We can see from the graph on the left-hand side that the insertion loss of the prime barrier and attached cylinder array are almost the same, except small differences which are originated from the geometrical differences of the barrier surfaces. If we plot the pressure and velocity field at the frequencies 125 and 211 Hz, which corresponds to the peaks of the insertion loss graph, we can see the harmonic standing wave patterns on the right-hand side of the barrier. It is more visible in the velocity plot. The white area are where the velocities becomes zero. And then we will examine the influence of the periodic resonators. The periodic resonators change the propagation characteristic of the sound waves propagating along the noise barrier. When the sound wave propagates along the horizontal periodic structure composed of a resonator unit, a guided mode can be generated on the surface. When the size of the resonator unit is small compared to the wavelengths of the sound waves, the dispersion relation of this guided mode can be derived by using the effective medium theory. By considering the interaction of the waves propagating above the structures and the resonator units, we can derive the dispersion relation of the waves propagating along the periodic resonators, shown on the right-hand side, and that can be represented as a graph shown below. The graph also shows comparison of the theoretical solution and the numerical solution. The theoretical and numerical solutions show good agreement. And the straight line below the gray region indicates the sound line, that is dispersion of the bulk wave in the air. For small values of kx, the dispersion of the guided modes follows that of the sound line, which means that the wave propagation characteristic is not that different from the one in pure air medium. But when kx increases, the frequency converges to the resonance frequency of the resonator. The slope of the curve drastically becomes small, reaching zero at the resonance frequency, which means that the wave velocity becomes slower. If we check the acoustic modes at certain wave number values on the graph, we can see that the wave fields are fairly confined at the surface of the resonators. Then we will go back to the insertion loss graph. The animation shows a pressure field around the noise barrier at one of the peak frequencies, 143 Hz. From the pressure field, we can see that the waves shows the pattern of the guided mode confined at the surface of the resonators. Another noticeable thing is that these wave patterns are the one of the standing wave patterns along with the vertical direction of the noise barrier, which indicates that the multiple peaks below the resonance frequency are due to combined effects of the guided mode generated by the nature of the periodic resonators and the standing wave modes around the noise barrier. If we check once again with the dispersion relation, 143 Hz is located here, and the slope at this point wave velocity is lower than the slope of the sound line. In other words, the wave velocity is slowed down compared to the bulk wave in the air. And due to the effect of the slow sound, the frequencies that correspond to such standing wave modes move to lower frequencies. So without the resonators, the same standing wave pattern should have appeared at this frequency. This slide shows the pressure and velocity field at 189 Hz. Again, we can observe the same phenomenon. On the dispersion curve, 189 Hz is located here, and the wave velocity is even slower compared to the case of the last slide. We also see that the confined field at the surface of the resonator is much stronger, and by this effect, the increase of the insertion loss is higher than the previous case. Likewise, without the resonators, the same standing wave pattern should have appeared at this frequency. Now we move up to the resonance frequency of the Helmholtz resonator. The pressure and velocity field show very different pattern from the previous cases. This wave behavior corresponds to what appears in the resonance gap of sonic crystals. In this resonance gap, sound energies are highly concentrated in the first few unit cells along the direction of the wave propagation and do not transmit any further. If we go to a little bit higher frequency, the waves interact only with the first resonator located at the top of the noise barrier. As the sound energies are localized at the resonators, the sound energy transmitted through the noise barrier can be significantly reduced. I would like to highlight that the physical origins of the sound attenuation in the yellow and green areas of the graph are very distinctive. The waves below the resonance are propagating guided modes along the periodic structures, whereas the waves above the resonance have evanescent nature. Based on the findings, we will introduce several design expansions of the noise barrier. If the resonators are placed on both sides, we can get higher increase of the noise reduction performance. The graph on the top shows the comparison of the insertion loss by the monolayer barrier and the double layer barrier. It also shows the insertion loss of nominal cases of the barrier with 0.2 meter and 0.4 meter, while the increase of the width for the nominal cases does not have significant impact on the noise reduction performance. The double layer barrier can reduce the noise significantly better than the monolayer case. The graph in the bottom shows the difference of the insertion loss compared to the nominal cases, and for the case of double layer barrier, the highest increase of the insertion loss is around 12 decibels. If the resonator with wider slit is used, the resonance frequency becomes higher and the insertion loss changes accordingly. In this case, the resonance frequency is located around 300 Hz, and we can also see similar patterns of many wiggles below the resonance frequency. If we put the resonators with different resonance frequencies at either side, the insertion loss of the whole system gives the combined effect of each side, which can be useful to achieve broadband enhancement of noise reduction. And similar double layer concept can be used while keeping single layer by alternating the opening direction of the Helmholtz resonators. In this case, effectively, the unit structure is the combination of the one resonator and one cylinder. The noise reduction performance of such structure is shown on the right-hand side graphs. As the last example, the periodic array can be placed along the curved structure, which can be easily found in realistic cases. Even though the resonators are placed in curved form, we can see that the same physical phenomena are happening. In the case of curved one, we could see higher increase of the insertion loss, reaching 10 decibels at the peak, and the higher increase is assumed to be happening due to the longer wave propagation path along the curved surface than the straight case. To conclude, we showed that a vertical array of periodically arranged resonators can be used to improve low-frequency performance of a noise barrier. We clarified the physical origins of the increased performance with the simplest case and showed several design examples. The future works will include experimental validation of the suggested noise barrier design and design of the new resonators for better performance, and investigation on the influence of surroundings such as ground and wind conditions. Lastly, I would like to thank Eurotech postdoc program for the funding support, and thank you for your attention, and I would be happy to answer your questions.